I am very happy to be able to introduce Dr. Deb Campbell from Lincoln Laboratory. I haven't actually worked directly with her in my time at Lincoln Lab, but we are both on the Climate Change Committee at Lincoln Lab, which is a very nice tie-in to Eric Evans' talk earlier this week. He talked about how some of the work we get assigned from government contracts. The other 50% of the work is work that we kind of say, this is a problem that needs to be fixed. And the climate change is one of those ways that senior staff come together and discuss ideas of things to fix and how we can fix them and how Lincoln Lab can help present solutions. So Deb's going to talk about quite a number of things today. She is in Division 2, and I'll let her describe what's in Division 2. What their mission is, but I'm very happy to present Dr. Deb Campbell for the seminar today. All right, Deb, all yours.
Great, Joel. Thank you. I appreciate the introduction, and it's great to hear that you heard from Eric Evans, our laboratory director, earlier this week. It nicely sets the stage for what I'd like to share with you today. So my name is Deb Campbell, and I'm a senior staff scientist here at the laboratory. And I've been here for 13 years, and I have a PhD in analytical physical chemistry. And I have worked in a number of different areas at the lab. I started off doing work more specifically tied to biology and chemistry, and spent some time in the director's office helping to manage the laboratory's internal research investment funding, and also strategic initiatives, new paths for the lab, and innovation at the lab. And from there, I moved on to co-lead the climate change initiative. And Joel suggested I tell you a little bit about the division that I'm in at the lab. I don't know if Eric Evans talked about our divisional structure, but I'm in a division called the Biotechnology and Human Systems area. And what we're all about, we have 4 groups in this division. One of the groups is responsible for protecting us against different types of weapons of mass destruction, particularly chemical and biological threats. And that can include man-made threats and also natural threats. We work in that area, and then we also develop novel chemical and biological sensing technologies. This could be something like in improving a sensor that can detect explosives better than a dog's nose. It could be detecting disease as a disease marker in someone's breath. So you have exquisite disease detection diagnostics. We also have a group that works on human performance systems, helping people be more understanding responses to stress. So one area would be heat stress. How does our body respond to heat stress, and how can we be more resilient to that through the use of wearable technology that can let you know how you're doing? And then I sit in the humanitarian and assistance and disaster relief group. And what we work on is kind of at the nexus of being able to respond to disasters and be more resilient to disasters. And now we're working in the areas of also climate change and human health, kind of that nexus. And, when you think about climate change, we think about it in terms of what the changes are, and then also how that is affecting our need to respond to more severe disasters, and how that has ramifications for our health as well. So what I'd like to do is give you a little bit of a background on climate change challenges, talk a bit about how we got where we are today, and some of the work that the laboratory is doing, and probably what Eric Evans emphasized is that we work on some of the most challenging problems and work on developing technology that can help address those problems. So I'm going to go ahead and share my screen. So, the question is, how did we get where we are today? And so I just wanted to do a quick background on the greenhouse gas effect. And this is a chart that shows what we would call a more normal situation in terms of our greenhouse gas environment on the left, and what the environment looks like as you get more greenhouse gases in the atmosphere. And what the chart's showing is solar radiation coming into the Earth and being absorbed by the Earth, and that heat is then re-radiated by the Earth as infrared light. And we have greenhouse gases in the atmosphere, and they absorb some of that infrared radiation, and that traps heat around the Earth. And that's actually a really good thing, because if we didn't have that, it would be too cold for us to live here on Earth. So we definitely need our greenhouse gases in order to have a habitable climate on Earth. But what happens is, if you get a lot more of those greenhouse gases in the atmosphere and you go more and more out of balance, you get more and more of that infrared light that's radiated by the Earth trapped. And so you get a lot bigger increase in temperature. And then that has a lot of ramifications, because it means that the land, the air, the water is getting warmer. And we can start to look at, how did we get here? And then what does that mean for us? And one of the things that we've been tracking for quite a while is what the CO2 concentration is in the air. And so there are some global observatories, and one of those is shown here on the right-hand side, the data that comes out of the Mauna Loa Observatory in Hawaii. And what you can see is a steady increase of CO2 concentration. And here it's being tracked from a little bit before 1960 until today. And you can go to this website and you can look at this. It's refreshed on a daily basis, but you can see that we are now over 400 part per million CO2 in the atmosphere. And if you look at the global mean temperature change that's plotted on the bottom, and this goes back further in time, because we can collect data from different sources a lot further in time on temperature. We can see that, there's a lot of fluctuation in temperatures, if we're looking 1850 up until right before 1950. But when the Industrial Revolution really kicked in, we started seeing a lot more CO2 in the atmosphere. And that increase in CO2 and that rise in global mean temperature, they parallel each other. And so you can see a direct connection between our activities and how we've gotten where we are on the greenhouse gas front. And the concern is that this also has a lot of secondary effects. We start to see changes in precipitation and more extreme weather. I think, you've seen in the news about flash floods that have hit the Northeast region of the country. You're also seeing heat waves, particularly in the southern part of the country. And some of that is also affecting our vulnerability to severe wildfires. So we're seeing that as well. And as the air gets warmer, we get more water in the air, and that leads to more intense hurricanes and tropical cyclones. We get greater melting of glaciers, and that's a challenge because, if you think about the Arctic, for example, when you have a lot of snow and ice, it's very reflective, but as that melts and you get dark water exposed, it has an amplifying effect. And that means that you're going to get even more melting. And so it's more of a cascading effect. And, there's a concern about reaching a tipping point where you really have much more severe melting and ramifications and sea level rise. The other concern, well, there's many concerns, but another one also is that the CO2 is absorbed by the ocean, and that can form carbonic acid. And the combination of the high temperature and the acidity is also really stressing coral. And so what I wanted to talk a little bit about today is some science and technology innovations that can address some of the climate change challenges. And I'm focusing a little bit more on sensing, because there's a lot of different kinds of technologies that we need. And some of the measurements that we want to think about, I just wanted to frame out a little bit. And so, what we'd like to do is better understand what's happening, be able to work on reducing greenhouse gases and addressing the impacts. And so, what we want to take a look at is, what are some of the things that we can measure? And one priority gas, in addition to carbon dioxide, is methane. There's others as well, but there's a lot of interest in being able to better understand methane and be able to reduce the amount of methane in the atmosphere. It accounts for, I've seen a number of different estimates. Some say as high as a quarter of the warming that our planet experiences today. And it has a 80 times as much global warming potential as CO2 does over a 20-year period. And so that's why methane is really being looked at as something that if we could go after methane quickly, we can have a big effect on controlling greenhouse gases and trying to minimize the temperature increase while we continue to work on reducing CO2 emissions and other greenhouse gases. So some of the things that we need to know is, is it coming from everywhere? Are there particular hotspots? And if we understand that better, then we can do a better job of controlling emissions. And in a lot of cases, we're going to want to know exactly how much methane is present, how it's changing over time. The other thing that we're very interested in is, understanding ocean temperature, getting a better handle on how that's changing. And there's other important properties about the ocean that we'd like to understand better, because global ocean circulation and understanding how that's changing is really important for climate modeling, weather forecasting, et cetera. And I think you've noticed, if you go to the ocean and walk through the water, even in a very small part of a beach, you can feel very different temperatures. And so when you think about the global ocean, there's a lot of temperature change across the world and even regionally in the ocean. So if we think about looking at measurements that help us better understand the current climate and how things are changing, that can help us control emissions if our measurements are focused on greenhouse gas measurements, and can also, if they're focused on the climate and the environment and how that's changing, the combination of those two can help us do a better job of modeling climate change and the future climate, because we need to understand what kind of trajectory we're on for greenhouse gas emissions. And then also we need to be able to do a good job of incorporating what's happening on the land, in the air, in the oceans, to be able to do that climate modeling, especially doing it at a more regional level, because what people would like to know is, what's going to happen in my backyard. So I wanted to touch on some of the sensing assets that are being used to look for methane. Again, that's a priority gas to reduce. And one asset is a sensor that's been developed by the European Space Agency, and it's on the Sentinel satellite. And this is one that's able to monitor the amount of methane and other atmospheric pollutants. And it's the first satellite that's designed to continuously monitor the planet for methane leaks. And this went up in the 2017 timeframe. And I think, the other reason I chose this is I really want to emphasize this is really there's a lot going around the world trying to be able to measure these greenhouse gases. And this is actually a priority for the UNFCCC, the United Framework Convention on Climate Change, and being able to measure, being able to get a handle on greenhouse gas emissions internationally. And so these measurements are going to be really important for measuring the baseline of where we're at, setting policy for how we're going to reduce greenhouse gases, and adjusting that policy as needed moving forward. So again, this is an example of the European Space Agency, and one of the things that happened not that long after this asset went up was that there was a massive leak of methane in the United States, in Ohio. And this was one of the first applications of that satellite And it was able to see this leak, to quantify the leak, and did it in a way that was independent of what the company was reporting as the impacts of the leak. And that's actually really important, to be able to have a way of measuring and verifying what is being reported by companies, because there's the bottom-up report by a company of, here's what we think we're releasing based on this information, and then there's top-down measurements that actually quantify what's being released. So that's a space-based asset, and there are other assets that are being developed today and coming on board. Some of these assets are on small satellite constellations. Some of them are airborne, and I'm going to talk about a airborne asset that the lab worked on. And I'm going to go into a little bit more detail about the lab's work now, and talk some about some remote airborne sensing that we're working on, and a little bit about ocean sensing. And the large satellites are really, really important for making measurements, and they're a massive player in this space. But there's also a move to constellations of smaller satellites that are less expensive to put up, and can give higher resolution data, which is actually really important as you're trying to figure out where these gases are coming from and what different countries are doing around the world. And also these can be smaller, lower cost efforts. And so I want to talk a little bit about some of the lab's work and other things that are happening. And then I'll talk a little bit about ocean sensing as well. And again, moving toward lower cost, more compact sensors, and trying to improve the spatial and temporal resolution, trying to get a better understanding of what's happening around the world as a function of time. And that kind of resolution is actually really important for our understanding and our modeling. So this example here is a very local example. So I went from looking at space now to looking at a very local example on the ground. And this is a case where the lab contributed some of its technology, working with a company called Bridger Photonics, to develop a novel LiDAR mapping system to detect methane leaks at different storage and fossil fuel producing facilities. And this is a system that goes on a UAV, an unmanned air vehicle, and it can sensitively image methane plumes. It can identify sources of the leaks and quantify the leak rate. And basically with the LiDAR, you get depth information, distance information from how long it takes your light to go from the source back to the detector. And then you can choose your wavelength. And in this case, they have a wavelength that's in the infrared range that's absorbed by methane. And what happens is that light intensity gets reduced by methane absorption, and then you can quantify how much methane is there. And the lab contributed to making this light source much more intense with a technology called the slab coupled optical wave amplifier. So this is great, if you want to get a very local measurement, so companies can use this and others can use this to go in and look very locally. But what is happening now is, as I said, these constellations of sensors that are being developed, and different types of optical measurements are being developed. One good example of this is the methane sat that's being developed by the Environmental Defense Fund. And that's with support from the Bezos Earth Fund. So this is really a massive project that's going to be bringing in the next generation of methane sensing capabilities. And there are other efforts as well. So again, there are international organizations working on this. There are US organizations. There are non-governmental organizations like the Environmental Defense Fund. So this is a really, really big priority, is to be able to do a better job measuring these greenhouse gases, especially methane right now, to be able to go after specific sources and be able to reduce them. I'm going to switch gears now and go to the ocean and talk a little bit about some of the work that we do on sensing in the ocean. And one of the reasons, well, there's a lot of reasons that this is really important. But what is particularly important is that the ocean is actually a reservoir for warming. And so a lot of the excess energy goes into the ocean, it's partitioned into the ocean. And this is because hydrogen bonded water has a very high heat capacity. So water is great at storing heat. And this heat gets stored, a lot of it goes into the upper ocean, which is the lighter blue curve shown here on the right. And then over time, that is transported to the deeper ocean. And this has a lot of implications for sea level rise, interactions in the cryosphere. So the cryosphere is in the Arctic and the Antarctic, where you've got the ice in contact with very cold water. And this has ramifications also for long-term ocean and atmospheric circulation patterns. And so better understanding the ocean temperature is super important, both in the upper ocean and also understanding what's happening in the deep ocean. So I wanted to take a minute and talk a little bit about some of the work that has gone on to date that is really cool and really, really important. And that is this international collaborative program for observing what's happening in the ocean. And it's based on the Argo float arrays. And this is a project that is a combination of exquisite sensing that happens on board ships. So that's shown here on the top left-hand side. And those kinds of measurements are really sparse. So if you want to measure the temperature at a given location in the ocean, you can drop down a sensor system and you can measure the temperature as a function of depth. And the challenge is you get a lot of accuracy, precision, but that's very sparsely done in terms of geography. And also that'll happen every few years in a given location. And so what scientists designed and came up with is something called the Argo float array. And this is super cool. What's shown on the right-hand side is the Argo float operation. And the idea is that there are these floats, and there's about 4,000 around the world. And each float will drop to about 1,000 meters. So it starts at the top and it's got an air bladder and it can adjust that so it goes down to 1,000 meters. And then it'll sit there and stabilize and then drop down to 2,000 meters. And then over the course of about 6 hours, it gradually rises back to the surface using that air bladder, and it measures the temperature and the salinity as a function of depth. And those are really important properties for understanding the ocean better and understanding ocean circulation and atmospheric circulation. So what has in place today, as I said, is about 4,000 of these, and they collect on a 10-day cycle, and they last for about 5 years. And there's all kinds of people all around the world, fishermen, other people that help keep this float array going. And what I did yesterday, actually, I don't have the latest one here. I looked at the one yesterday, but I didn't pop it in here. But you can see today there's almost the same number of floats at almost the same locations in 2023. But if you search Argo float, you can go ahead, get on their site, you can see where they are today, you can see what kind of data they're collecting. And this has been wonderful for getting a better understanding of the ocean. One of the very recent efforts with this is what's called the Deep Argo Float Array. And so this has been developing this same kind of sensing system, but to go twice as deep, to go down to 4,000 meters, so we can start better understanding what's happening deeper in the ocean. And there's more than 69 of these out there now, but the goal is to get to around 1,250 or so, and they have gotten a big plug of funding to be able to build that array out further. Some of the challenges are, even though this map looks really dense, it's a map of the world. So these sensors are still pretty far apart, and we don't get the spatial and temporal resolution that we would really like to get. And one of the things that the lab has been working on is building fibers. We have something called the Defense Fabric Discovery Center here at the lab. And what we're doing is taking these very narrow polymer fibers and building arrays of sensors into those fibers that can measure lots of different things depending upon what kinds of sensors you build into the fibers. So far, we have embedded temperature sensors and the fiber is a function of depth. So you can drop that down into the ocean and you can measure the temperature at all the depths at the same time continuously, which is really different than measuring it every 10 days and doing it as the Argo float is rising. And so there are definitely a lot of different kinds of applications for this. And now what we're working on is adding the ability to measure salinity and other ocean parameters to this. So this is work that's the Argo float array is not lab work. It's very important international work. But the ocean fiber sensing work, that is something that the lab is working on and contributing. And we actually participate in, the Navy has an ice exercise in the Arctic every 2 years. And the laboratory participated in that in 2022, and we will be in 2024, bringing different types of sensors to measure the Arctic ice melt and property changes that are happening as the Arctic ice is melting to look for tipping points. And this sensor array is one of those capabilities that has gone to the Arctic as part of the sensor array that the team took. So we're pretty excited about this. So I want to step back for a second and be a little bit more general about some of the climate change challenges that we face, the technologies that we need. I talked a lot about sensing, both greenhouse gas sensing and ocean sensing, but want to step back and take a more holistic view. And this is how the laboratory is thinking about climate change challenges, looking at what kinds of things we can do to help address those challenges. And we do have a website if you want to, an externally facing website. If you want to check that out, I have the link here. You can just find it by searching Lincoln Laboratory Climate Change. But one of the most important things, of course, that we need to do is mitigate the drivers of climate change. So that means, we want to work on reducing greenhouse gas emissions. And there's a lot of different ways that we can do that. And we are working toward that in the country and around the world. It requires a lot of change across a lot of different sectors, personal changes. And so, this is something that is evolving over time. And so, obviously you see a lot more electric vehicles available, a move to renewable energy. There's a whole host of things that are happening that we can contribute to and support. And at the same time that we're working to drive down greenhouse gas emissions with changing a lot of our activities, we need to be able to measure them. And so that's why I started there, because that's actually really important for mitigation. You need to know where the emissions are coming from. And as we change our policies to try to drive those emissions down, we need to figure out, well, how well are we doing? And we don't only want to know how well the United States is doing. As you guys know, this is a global problem. So we want to be able to understand how well are things going around the world. And this is really a big focus of the Council of Parties, the COP meeting that happens every year. We have the Paris Agreement in place. And there's something going on now that started at the COP26 in Glasgow, which is the global stock take. So countries that have signed on have given nationally determined concentrations that they're going to hit for greenhouse gases. And that is being monitored by these countries, with bottom-up estimates. And there's going to be a report out on that global stock take at the COP28 meeting that's coming up in Dubai this late November, December, to see how we're doing. So at the same time that that's happening, we are working on improving our greenhouse gas measurements so we can monitor what's actually happening. And so those measurements will see, wow, how are we doing with what we have in place? How do we need to change policy? So it's really a pulse check of how we're doing. And so the laboratory works a lot on novel sensing capabilities for greenhouse gas sensing. So we're working on one now that is able to, it's an airborne platform, and it flies in a way that allows it to look at very wide areas, but with high resolution. So it's like a good combination of satellite capability, wide area, but higher resolution, more like the LiDAR system that I showed you. So really trying to hit that sweet spot so that you can more efficiently and sensitively gather that information. The other thing that we need to do better on is, observing the climate and understanding how the climate's changing. That can improve our ability to model the climate, but also really importantly, it can help us understand tipping points. Is situations where we're really moving toward a significant change, and we need to start preparing for that. Also really important is being able to predict climate change. So we do have fine resolution models. Those models are being AI enabled more and more because they're so computationally intensive that there's lots of different approaches to minimize the computational intensity of those models, and AI can play a key role there. So there's a lot of active research in that area. And what we are also doing is being able to predict the impact of climate change. How is it going to affect food and water security? How is it going to affect people's livelihoods? How is it going to affect where you live? And also adapting to impacts is really important. And I think you can kind of see the balancing act between the more we mitigate, the less of an impact climate change is going to have. And so the less we're going to have to adapt. The less we mitigate, the more pressure it's going to put on the need to adapt. And the last thing I want to mention also is that not only do we want to reduce the amount of greenhouse gases we're putting in the atmosphere, but what if we could draw down what's already there? And so there's a lot of work that goes on in the area of carbon capture and storage. And then there's also interest in different ways of managing solar radiation, doing sun shielding, other types of things to try to minimize the warming that way. And I talked about one way that we're applying laboratory capabilities, and that is through improving our ability to monitor the climate, monitor emissions. And now I'd like to talk a little bit about building next generation forecasting and decision support tools. And this is really important because it's incredibly helpful to have a better understanding of what kinds of climate change you might experience in your backyard, a country might experience in its most vulnerable regions. And that can help inform how do we adapt to climate change. And I think if you look around today at a lot of the challenges we're facing with wildfires, with heat stress, and in some of the most vulnerable regions of the world where they don't have the resources to begin to adapt, we're not really well adapted today, let alone to what's coming in the future. And so if we could better understand what's coming in the future while we work on adapting to what's happening today, we should also be working on adapting to the future. So you don't want to look back in time and say, wow, hurricanes have occurred with this peak wind speed, so I should build my house to manage that peak wind speed. When if you look down 10, 20, 30 years, the wind speed is going to change so significantly that if you build to today's code, you're not going to be resilient to 10, 20, 30 years out. So you really want to be looking forward with the actions that you're taking today. And so I want to finish up with talking about vulnerabilities around the world and a really major project that Lincoln Laboratory is working on with our campus colleagues. And this project's motivated by the pressures of climate change on really vulnerable populations around the world. And, I'm sure you're well aware, of course, that the more industrialized countries like the United States, China, and others have been the major greenhouse gas polluters. But then there are countries that really have minimally used fossil fuels, but are maximally impacted by climate change. And this is in Africa, it's in South Asia, it's in Latin America. And even if we improve our ability to drive down greenhouse gases, adaptation is still required. And there are some hotspots that are really under severe stress. And that kind of stress can destabilize areas of the world that are already fragile. It can lead to intergroup conflict, destabilization, and that's really a challenge for our national and global security. So there's really a globally recognized need to better understand risks in really vulnerable parts of the world and help with resilience planning. And so when we think about what this might look like, what does a climate resilience decision support framework look like? What we'd like to be able to do is understand what are the local effects, and we're talking about with a 10-kilometer or better resolution. So really trying to understand, what's happening in my town, what's happening in my backyard. And depending upon where you are in the world, you could be looking at heat waves or droughts or sea level rise or increase in storm intensity. And you want to take that information and understand, well, what are the human system impacts? How is this going to affect the loss of where I can live? Can I live where I am? Am I going to need to move? How does it affect my livelihood? Can I keep working the way I have been? And to adapt to change, you need solutions. And there's a lot of different types of solutions that can help people adapt to change. And you need to identify what those are. And you need to make sure that they're effective and impactful and share that information. And decision support systems are a way to share that kind of information with local communities and governments. And so we have a team that we brought together with strengths across all of these needs. And we have all our logos here, and Lincoln Laboratory is in the middle with the LL and the Lissajou pattern in the middle. And we're kind of the project integrator. We're bringing the project together, and we have expertise in developing decision support systems. And a great example of that is the Federal Emergency Management Agency has a hurricane evacuation system called HUREVAC. And that is what over 12,000 emergency managers in the US use to help people understand when they need to evacuate where. And that is a system that Lincoln has put together and is being used today. And we can use that type of approach to develop other kinds of decision support systems like a climate resilience system. And what we need to do is pull in all of the exquisite modelings, climate modeling, socioeconomic modeling, and climate impact modeling, and understand what is going to happen in a particular region, what kinds of interventions are needed, and share that information. And we're working with JPAL, which is the Abdul Latif Jameel Poverty Action Lab on campus, as part of this effort to look at the effectiveness and impact of these interventions to make sure that they are effective and impactful. And they're a great partner on this as well. The two professors on campus that are leads of JPAL, Professors Duflo and Banerjee, won the 2019 Nobel Prize in Economics for doing just this type of work. And so we're very fortunate to have people from their team working with us. And then I didn't say the names of the other centers on campus, but we work with the MIT Center for Global Change Science and faculty and researchers there. And then also with the MIT Joint Program on Science and Policy of Global Change. And we're working in Bangladesh, one of the most climate vulnerable parts of the world. So you can see in the map here, Bangladesh is on the Bay of Bengal, and it has a lot of vulnerability to tropical cyclones in the coastal region. And they experience a whole myriad of climate impacts, from sea level rise to worsening cyclones. You've got droughts in the north, you've got severe flooding near the rivers, they have heat waves. And I want to emphasize also, because we really focused on climate change, but it's really, you have to think about climate change, population increase, where people live. There's a tendency of people to live closer to the coast, in cities. And so a lot of pattern of life also makes adapting to climate change quite challenging. And in Bangladesh, where we're working to help with adaptation, we're working very closely with an on-ground partner called BRAC, which is a non-governmental organization. And BRAC was founded at the same time Bangladesh was, in the early 1970s, and has worked hand in hand with the government to develop different types of social and humanitarian efforts, including water, hygiene, agriculture programs, educational programs, climate microfinance programs. And they also have a climate adaptation program, but a lot of the work that they've done has been looking at what happened in the past. And now we're working with them to bring together all that research on campus in a way that they can understand it and make it operational in the country, so that they can work on proactively adapting to the climate change that is coming down the road, but start really working on adapting today. So this is one of MIT's 5 Climate Grand Challenges projects. And again, we're bringing what's regional climate and impact forecasting and interventions to decision makers. And we're working in Bangladesh, and then we also have a pilot in East Africa and Sudan. And just to give you kind of an idea of what types of interventions we're looking at cyclone and heat resilient housing. And an example of what they're doing now is shown here in this slide. But there's some challenges with it, and it's actually a really expensive house to build. And so we're looking at, what types of alternatives could be super effective and impactful against sea level rise, heat stress, and the winds of future tropical cyclones. We're also looking at a really challenging problem in the southwest part of the country with salinity intrusion, which is a severe threat both to water security and food security. And so we're looking at opportunities and interventions for water harvesting and changes in agriculture and aquaculture that will help people be more climate resilient. And I think another interesting thing, I'm going to just jump back one slide, and it's there's the city of Dhaka, which is in the center of this map, and that's a city that has grown massively in Bangladesh because of climate change. People are migrating in addition to trying to adapt where they are, and there has been massive migration to Dhaka, and Dhaka has outgrown its ability to take new people in. I think there's well over 1,000, it's between 1,000 and 4,000 people a day are going to Dhaka. And so the country is also working on a climate Migrant Resilient Cities and Program Plan. And we're working down in the southwest corner. And if you go a little bit north, some of the first writing you'll see is Manglaport. And that is the first climate resilient city that they are working on in country. And so for the area we're working in, that is a region where some people who probably will be displaced from climate change are looking at migrating to. And we can help inform where those resilient cities and towns should be and what kinds of things they can do to be more resilient so that they're prepared for climate migrants to come there, because people really want to migrate more locally. They really would like to stay as close to home as possible. So there are 20 different sites that are intended across the country for this to take the pressure off of DACA. So the last thing I want to leave you with, so we have some time for questions, is just kind of a one over the world on MIT's Climate Grand Challenges. This was a call back in 2020 to deliver a whole of MIT initiative to come up with high impact climate solutions for the world. And there were over 100 ideas that came in. 27 teams submitted phase 2 proposals and 5 flagship projects were selected. And CruiseNet, the Climate Resilience Early Warning System Network that I just shared with you, is one of those 5 flagship projects. So we kicked that off a year ago. And again, we're working on in Bangladesh and Sudan. And this is just kind of a one over the world slide. That emphasizes we're empowering communities to better plan for and respond to climate change, looking out the next 10, 20, 30 years. And what I'll leave you with, and I don't know if you have seen this before, is just a quick snapshot of the 5 Climate Grand Challenges. Has anybody shared this with you? Because I'll just talk about it for a minute.
Yeah.
So have you seen it already?
No, we have not seen that yet.
Oh, okay, great. So this is just kind of an overview of what rose to the top for the 5 flagship projects, just so everybody knows. I talked about CruiseNet. One of the other really severe challenges we're facing is weather and climate extremes around the world. So as the planet is warming and we have more moisture in the air, we are finding a lot more extreme conditions. And so being able to better understand what is coming and being able to prepare for that is really, really important. So there's a lot of work going on, especially focused on urban environments. And the work is also coupling into accelerating the transition to low carbon resources. So really driving adaptation and mitigation together. There's another one called Bringing Computation to the Climate Change Challenges. And this is taking novel approaches to modeling, creating smaller and more localized models that can be run more easily and are less costly to run, so that stakeholders have greater access to being able to use them and gather information from them. There's another one which is revolutionizing agriculture with low emissions resilient crops. So this team is working on seeds that are self-fertilizing and more climate resilient, so they're more drought resilient. This will greatly reduce the use of fertilizers, and fertilizers actually contribute significantly to greenhouse gas challenges, especially in making them. And that's a nice lead into the Center for Electrification and Decarbonization of Industry called SETI. And there's teams on campus that are working on big industrial problems, new ways to decarbonize the most carbon intensive industrial materials production sectors, and that's steel, cement, ammonia for fertilizer, and ethylene. And these sectors alone have been estimated for being responsible for about 1/3 of our greenhouse gases. So, being able to decarbonize is super important. So that's the last slide I have, and I definitely want to open it up for questions. And I see a ton of stuff that came in on the chat. And
Thank you, Dr. Campbell. I think
yes.
we'll have time for, do have a few questions. We'll alternate between online and in person here. I do want to add that I hope that the courses both the virtual courses and the courses here all saw an application in what Dr. Campbell was talking about, from autonomous vehicles to sensing, CubeSat, you saw satellites, and certainly data science. The data science projects that are going on with some of our courses. Nothing happens in things like CruiseNet that Dr. Campbell talked about without that data science going on behind that. So I hope you kind of all thought about applications as she was talking about what we're doing here. Also a question for the students. How many of you know that MIT announced a climate major this year?
Good point.
So there is a climate major at MIT this year, and I think more and more universities will be having those. And it's just cross-cutting a lot of different engineering disciplines. As you can see in Deb's talk, that the number of disciplines involved in building something like that is just everybody's got to be involved to do that kind of big system, build that up. So, yeah. And one more question. How many of the students would like to see a climate data analysis course here at BeaverWorks next year? All right. All right, so we're going to handle questions here, and then I'll switch to Lisa to ask questions online. So right here in the gray sweatshirt. I'll repeat yeah, go ahead.
Thank you, Dr. Campbell, for the very informational presentation, especially the focus on global impact on policy. I find it really sad that we are preparing for the consequences as much as trying to prevent them, if not more. So what are your recommendations for us as the younger generation to act right now to help with the cause? How do we act fast to help with this global emergency?
I think that's a great question. And I think right now, looking at what our administration is doing, trying to set policy, trying to put funding in place to drive down greenhouse gas emissions is really important. I think that, we can make changes and decisions in our lives and how we live. We can advocate with our vote and advocate with activities in our communities and advocate nationally and globally for what we think are the right things to do. So I think a lot of it is coming together, advocating, and some of the, I think that there has been some denying of the science, but I think the impacts are getting great enough that people are more and more coming on board with the need to address this. There's a lot of people that are entrenched in the fossil fuel industry. It's a difficult transition, but we really have to be full force behind pushing that transition in a way that is effective. It is disruptive to push that transition, but that is what needs to happen.
In short, get involved.
Get
Lisa,
involved.
From
Yep.
the online group.
Si-Chan Wang, do you want to ask your question?
Thank you very much for the talk. And I'm wondering, since you mentioned that the Argo floats are operated by people around the world, including fishermen, is it possible to expand this citizen science effort in crowdsourcing data to provide more complete data?
That's a great question. Crowdsourcing data and thinking about different kinds of data that you can collect is huge. And this I can think of lots of different ways to do this. So yes, I mean, that is a possibility on the ocean front. Need to think about how the community would do more of that, whether it would be more floats, quite what it would look like, but yes. And one of the areas that I think there's really fascinating work going on in there's a kind of a new term, hyper-local data. And to the point of, if you want to, there have been wearable air quality sensors, particle sensors. There's to the point where people can wear a sensor and share that information, and it can see exactly where you are and create this really detailed map of what's happening in a city or community. Obviously, there are privacy decisions there, and you'd have to want to participate, but you can also have hyper-local sensing where it's an infrastructure that you put in that's not on people, but it can provide exquisite information on urban heat islands, air pollution, all of that. And that's going to be really, really important information to improve our resilience moving forward. So there's definitely a lot of places for citizen science and posting that information so everybody can see it. A lot of times when you get these big data sets coming together, there can be commercial entities behind that. And this is even happening with greenhouse gas mapping. Some of it's behind a firewall. There's a paywall, like big companies can afford it and not everyone can see it. So doing it in a way that is open source so everybody can see it is the right way to go.
Okay, we have another question from the audience.
Hi, thank you for the presentation. So I saw in the MIT newsletter, I think maybe a month ago, that about this the new program regarding climate change, and I believe it's like sort of the intersection of climate change and civil engineering. And I'm just wondering, do you think that this new program, like the combination of those two things, will sort of go well together? I'm just curious as to your opinion about that.
I definitely think that goes well together. I can see so many different ways it could go together. You know, when you think about civil engineering and all the challenges we face with redesigning buildings, using green cement, making our cities less vulnerable to heat stress, you know, even thinking about when and where you can build based on climate. I mean, right now, if you look at Phoenix, construction workers can't be out during the day. You've got to work when it's cool. And right now it's never cool, but schools are closed, you know, and they need to work on schools during the summer. So there's going to be all kinds of challenges and innovations that are going to be needed in going greener, going greener to address mitigation, being more adapted to the changes, because we're going to need to do both. So I think it's a real sweet spot.
I think we're going to take another question from online, and then we'll probably get to, or have to wrap up. Dr. Campbell, what we'll do is we'll actually send you the list of questions in the chat as well for later. And
Yes.
then we can try and close out and get the students back to class here. Go ahead, Lisa.
Meryl Zhang, do you want to ask your question?
Oh, yeah. Sorry if you can hear the phone.
That's okay. I can hear you.
Which of the greenhouse gas sensing methods would you say is the most cost effective and also accurate?
That's a good question. Because you do want to think about cost effectiveness and accuracy, because if you are going to, you know, call somebody out, you really need to make sure that your measurements are accurate. I don't, and it depends upon which gas you're looking at. So we don't have a cost-effective, accurate method yet. We don't have that sweet spot. That is what we're headed toward. And I think that with the constellation of satellites that are lower cost, that have better resolution and better accuracy, we are moving in that direction. So I can't give you a specific example. That is really a very active area of research and much needed. So sorry that I don't have like a more, we're not there yet is the answer.
Okay,
So
thank
our
you.
teacher presenters for today are from remote sensing. Nathan, will you want to mention your thank yous, and then we'll go to Anshul.
Yeah, sure. So I just wanted to say, like, thank you so much, Dr. Campbell, for the interesting talk today. And I think we all learned a lot about like climate change and the various technologies that everyone has like worked on to combat climate change and greenhouse gas emissions. And something that I found really interesting and exciting was the use of like the satellites to detect the greenhouse gas emissions, like the methane leaks, and the use of like the floats and the nets to gather like ocean data. And I feel like what you talked about today closely relates to what we are learning in our remote sensing for disaster response class. And I feel like these technologies have a huge potential to keep greenhouse gas emissions in check and benefit the world. So thank you so much for your talk today.
You're welcome.
I just want to echo what Nathan said. Thank you so much. We really appreciate the overview of all the technologies that your lab has been working on, especially talking about the international partnerships and the policy behind reducing emissions. I especially thought the Argo Float project was really interesting and how it's like a global effort to maintain this entire network and better understand the ocean. For your talk and for all your time today, we wanted to present the Beaverworks shirt for you. I think
Awesome.
I should have something.
Yeah, that's great. Thank you so much. I don't have a Beaverworks shirt. I've always wanted one. Thank you. It was great to be here with all of you today, and I look forward to seeing the rest of your questions and getting back to you on those. So thank you so much.